Welcome to this quiet space, a place for gentle stories from the heart of science, designed to help your mind wander as your body finds rest. Tonight, we begin a journey together into the story of a force you have known your entire life, an invisible presence that holds you now, even as you begin to drift. We will explore the story of gravity, the unseen force that cradles your dreams. Before we settle in, I would love to know where in the world you are listening from tonight, or perhaps something gentle about your day. You can share it in the comments below. And if you find a little peace in our time together, please consider supporting this space with a like and a subscription. Your kindness helps these stories find others who might need them. Thank you so very much. And now, let us begin. Let your awareness settle, just for a moment, on the simple feeling of your own presence. Notice the gentle pressure where your head meets the pillow, a soft yielding, a sense of being held. Feel the weight of the blanket as it rests upon you, a subtle but constant reassurance, a quiet heaviness that speaks of comfort and of place. This feeling, so intimate and so familiar that it often goes unnoticed, is your first and most personal connection to one of the deepest truths of the universe. It is the touch of gravity, the silent, invisible river that flows through all things, pulling the cosmos together in a slow, unending embrace. You do not need to look to the stars for evidence of its power. You feel it now, in the gentle surrender of your body to the bed, in the quiet certainty that you are anchored, safe, and still. This sensation is a form of knowing, a physical wisdom your body possesses called proprioception, the silent awareness of where you are in space, a sense woven from the constant, faithful pull of the earth beneath you. It is a whisper from the very heart of our world, a planetary lullaby that has soothed every being that has ever rested upon its surface. This force is not an intrusion, but a foundation. It is the reason the air itself stays near, forming the soft atmosphere we breathe, and the reason the oceans do not fly off into the void, but instead are held in their deep, rhythmic slumber. And as you lie here, feeling this gentle terrestrial insistence, allow your imagination to drift outwards, beyond the walls of your room, beyond the quiet sky of night. The very same influence that gives your blanket its comforting weight is, at this very moment, performing a silent and majestic dance on a scale that defies comprehension. It is this same pull, magnified by an unimaginable degree, that reaches out across 238,000 miles of silent, empty space to hold our moon in its perfect, ceaseless orbit. The moon, in turn, with its own lesser but still potent gravity, reaches back to our world and gently pulls upon the great oceans, coaxing them into the slow, rhythmic breath of the tides. There is no string, no visible connection, only this invisible, far-reaching, timeless certainty. What is the source of this power? It is simply the presence of substance, the reality of matter itself. The principle is profoundly simple. Anything that has mass, anything that is made of stuff, exerts a gravitational pull. Your own body, the bed you are resting on, the earth, the moon, the distant, silent sun, all are participants. More mass creates a stronger pull, a more insistent call across the cosmos. The sun, with its immense substance, calls our earth to circle in a patient, year-long journey. Our earth, in turn, whispers to you, holding you gently to its surface. And even your blanket, with its small and humble mass, offers its own tiny whisper of gravity, a presence that is real, even if it is too faint to feel against the overwhelming embrace of the world beneath. It is a universe of connections, a web of silent invitations, where every object calls to every other, and you, resting here, are part of that cosmic chorus. And in this silent, universal pull, we find the first and most constant embrace of the cosmos. That same constant embrace that holds the planets in their silent dance has also been a patient, silent architect, shaping the very form and flow of life on our world. Gravity is not merely a force that governs rocks and stars. It is the unseen sculptor of the living, the silent partner in the long, slow story of evolution. Imagine a single tiny seed, dormant in the cool, dark earth. It holds within it a blueprint for life, a dream of sunlight and sky. but it is gravity that gives it its first direction. Even in the complete absence of light, the seed knows which way is down and which way is up. A nascent root, responding to this perpetual signal, delves deeper into the soil, seeking water and stability. This response, this innate sense of direction, is called gravitropism, a plant's primal orientation in the world. The growing stem, in an act of beautiful defiance, pushes upward against that very same pull, reaching for the energy of the sun. Think of a great and ancient tree, a mighty oak or a towering redwood. Its entire structure is a testament to a lifelong conversation with gravity. The strong, woody lignin in its trunk, the vast network of its anchoring roots, the very shape of its branches reaching for the light, all are expressions of a perfect balance struck between the upward thrust of life and the downward pull of the earth. It is a living sculpture carved by an invisible hand. From the quiet, rooted world of plants, this gravitational influence flows into the very design of our own bodies, and those of all creatures who walk, crawl, or swim upon this earth. Our bones are not inert scaffolding. They are living, dynamic tissues that respond constantly to the demands placed upon them. The reason our skeletons are strong, dense, and resilient is because they have grown in a field of gravity, perpetually bearing our weight. Astronauts who spend extended periods in the microgravity of space must exercise rigorously, yet they still experience a loss of bone density, a subtle fading of their physical foundation, because their bodies are missing that constant grounding stress. Our hearts, too, are powerful muscles, precisely because they must work against gravity, with every single beat, pushing blood upward to the brain, defying the downward pull to sustain our consciousness, our thoughts, our dreams. This ever-present force has defined the blueprint of our existence, a silent pressure that has forged our strength. It has set the fundamental rules of scale for life itself, a principle known as the square-cube law. As an object grows larger, its volume, and therefore its mass, increases much faster than its surface area or the cross-section of its limbs. This is why a tiny mouse can fall from a great height and walk away unharmed, while a creature as large as a horse would shatter its bones from a similar fall. Gravity places a gentle but firm limit on the size of life on land, ensuring that for every form, there is a perfect balance between substance and strength, a design honed over eons to exist in harmony with our planet's embrace. And this influence extends even beyond our individual bodies, shaping the very environment that sustains us. The soft, breathable air of our atmosphere, the delicate ocean of nitrogen and oxygen, does not drift away into the void of space, because gravity holds it close to the Earth's surface, creating the atmospheric pressure that is essential for life and for liquid water to exist. Gravity pulls the rain from the clouds to nourish the land, feeds the rivers that carve the canyons, and holds the world together in a way that allows for the breathtaking complexity of a living, breathing biosphere to unfold. It is the unseen sculptor of the living world, the silent partner in every breath and every heartbeat. It is the unseen sculptor of the living world, the silent partner in every breath and every heartbeat. And for millennia, this partnership was a truth felt only by the body, an unspoken agreement between life and the world it inhabited. But the human mind, in its quiet and relentless curiosity, could not help but look up and look down and wonder about the nature of this insistent pull. Long before the language of mathematics could describe it, the language of philosophy sought to give it meaning, to weave it into a story of the cosmos that felt harmonious and true. In the sunlit academies of ancient Greece, the great thinker Aristotle imagined a universe not of forces, but of desires, of a natural order where everything knew its proper place. For him, a stone dropped from the hand did not fall because it was pulled, but because it yearned to return to the earth, its home. Smoke from a fire did not rise because it was light, but because it was airy in nature, and it sought to rejoin the sky. Everything in this terrestrial realm, earth, water, air, and fire, had a home, a natural level in the hierarchy of the world, and all motion was simply the result of things seeking their rightful place, a cosmic settling into a state of perfect rest. It was a beautiful, intuitive, and deeply personal vision of the cosmos, one that placed our own world and ourselves at the very heart of the story. This feeling of a central, special home was reflected in the grand architecture of the heavens they imagined. The earth, they believed, lay still and unmoving at the center of all things, while around it, in a series of vast and perfect crystalline spheres, the celestial bodies made their eternal journey. First came the sphere of the moon, then Mercury, then Venus, the Sun, Mars, Jupiter, and Saturn, and finally, the great sphere of the fixed stars, a dark, glittering dome that enclosed the whole of creation. This was the Ptolemaic system, a universe of divine perfection and flawless geometry, a cosmic cathedral built around humanity. In this model, the heavens were made of a fifth perfect element, the ether, and they moved in the most perfect of all shapes, the circle. There was a profound and comforting duality to this vision, a chaotic, changeable, and imperfect earth below, and a timeless, predictable, and perfect heaven above. This story resonated for over 1,000 years, for it spoke to a deep human need for order, for meaning, and for a universe that was built with us in mind. But even in this perfect clockwork, there were subtle, troublesome mysteries. 5 of the lights in the sky were not fixed like the stars. They wandered. Indeed, the very word planet comes from the Greek word planetes, meaning wanderer. These wandering stars would drift patiently across the sky, but then, inexplicably, they would slow down, stop, and move backward for a time before continuing on their forward path, a strange celestial hesitation known as retrograde motion. To account for this deeply imperfect behavior within a system built on perfection, astronomers devised ingenious solutions, imagining that the planets moved in smaller circles, called epicycles, which in turn were carried along on their larger circular orbits, a system of wheels upon wheels, growing ever more complex to save the beautiful, simple story of an Earth-centered cosmos. And in these complications, in these tiny, persistent anomalies, lay the first whispers of a far grander and stranger reality. In these complications, in these tiny, persistent anomalies, lay the first whispers of a far grander and stranger reality. A reality that would require not just a new map of the cosmos, but a new way of seeing altogether. For centuries, the story of the universe had been read from ancient texts and reasoned through pure logic, but a new kind of courage was beginning to surface in the human spirit. The courage to let go of the most cherished stories and instead to trust the quiet testimony of the world itself. This new way of thinking found its voice in the mind of a brilliant Italian astronomer named Galileo Galilei. He was not content with the ancient explanation that heavy objects fall faster than lighter ones because they have a greater desire for their natural place. So, he began to experiment, to ask questions of the world through observation. Legend tells of him climbing the famous Leaning Tower of Pisa, dropping 2 spheres of different masses to see which would land first. While this story may be a myth, the truth it represents is profound. Through his careful experiments, rolling balls down inclined planes to slow their descent and measure their motion, Galileo discovered something that defied 2,000 years of intuition. All objects, regardless of their mass, fall at the same accelerating rate, provided you can discount the gentle resistance of the air. A feather and a cannonball, dropped in a vacuum, would arrive at the ground at the very same moment. This was a radical idea, a profound shift in perspective. Gravity was not a desire inherent in an object. It was something external, something that acted upon all objects equally and democratically. This courage to observe was not confined to the world below. Galileo had heard of a new invention, the telescope, and he set about building his own, pointing it toward the heavens to see what secrets it might reveal. And what he saw in the silent, winter nights of 1610 would shatter the crystal spheres forever. When he turned his gaze to the great planet Jupiter, he saw not 1, but 4 tiny points of light accompanying it, 4 little stars that moved with Jupiter through the sky. Night after night, he watched them, mapping their dance, realizing he was witnessing 4 moons in orbit around another world. Here was undeniable proof that not everything in the universe circled the Earth. The ancient model, with our world at the benevolent center of all motion, was broken. He looked at Venus and saw that it went through phases, just like our moon, a changing cycle of light that could only be explained if Venus itself was orbiting the Sun, not the Earth. He looked at our own moon and saw not a perfect, ethereal sphere of ether, but a rugged, textured world with mountains and valleys, a place as imperfect and as real as our own Earth. He dared to look at the Sun and saw dark, shifting sunspots on its surface, blemishes on the face of perfection. The comforting, ancient distinction between the corruptible Earth and the perfect heavens dissolved in the light of his observations. It was all one universe, a single reality, likely governed by a single set of laws. But if the Earth was not the center, if it was in fact a planet moving through space, then a great question arose. Why do we not feel the motion? Why are we not all swept away by a great wind as our world rushes through the cosmos? Galileo provided the answer with another revolutionary idea, the principle of inertia. An object in motion, he reasoned, will stay in motion unless acted upon by a force. We, and the atmosphere, and the clouds above, are all moving together with the Earth, sharing in its motion, and so we feel no different than a passenger on a smoothly sailing ship who feels no sense of movement on a calm sea. The old story of the universe was fading, its foundations removed one observation at a time, leaving a profound and unsettling silence, an empty space where a new story, a universal story, was waiting to be written. The old story of the universe was fading, its foundations removed one observation at a time, leaving a profound and unsettling silence, an empty space where a new story, a universal story, was waiting to be written. Into this quiet moment of scientific history stepped a mind of unparalleled genius. Isaac Newton. He inherited the scattered pieces of a cosmic puzzle, the meticulous planetary observations of Kepler, the foundational insights into motion and inertia from Galileo. And within his mind, these disparate ideas began to converge, drawn together by a single, revolutionary thought. The legend that has come down to us is one of sublime simplicity. Newton, sitting in a garden, sees an apple fall from a tree, and in that mundane, earthly event, he saw a connection to the grandest celestial motion of all. He looked from the falling apple up to the moon, held in the pale daylight sky, and he asked a question that would change the world. If gravity is the force that pulls the apple from the branch to the ground, could it be the very same force that reaches out and holds the moon in its orbit? Perhaps the moon, too, is falling, constantly falling toward the Earth, but it is moving so fast sideways that it continually misses, forever circling in a state of perpetual descent. This was the great synthesis, the moment of profound unification. The laws of the heavens and the laws of the Earth were not separate, they were one and the same. The force that governs the smallest fall is the same force that choreographs the dance of the planets. With this powerful insight, Newton set out to describe this universal force, not with philosophy, but with the elegant and unambiguous language of mathematics. He proposed a law, a single sentence of cosmic grammar, which we now call the law of universal gravitation. The law states that every single particle of matter in the universe attracts every other particle. The strength of this attraction, he calculated, depends on two simple things. First, it depends on the mass of the objects involved. More mass means a stronger pull. The Sun's immense mass keeps the Earth in its orbit, while the Earth's more modest mass is what holds the falling apple, and you, and the Moon. Second, and this was the secret ingredient, the force depends on the distance between the objects. But it does not simply get weaker with distance. It does so in a very specific, very beautiful way, a relationship known as the inverse square law. To picture this, imagine a single candle burning in an immense dark room. The light from its flames spreads out in all directions. If you stand 1 foot away, a certain amount of light reaches your eyes. But if you move to stand 2 feet away, that same amount of light has spread out over 4 times the area, and so the light you see is 4 times dimmer. If you move 3 feet away, it is 9 times dimmer. The intensity of the light fades in proportion to the square of the distance. Newton proposed that gravity works in precisely the same way. Its influence radiates outwards from an object, thinning out, becoming more gentle and diffuse across the vastness of space. This elegant, simple law was astonishingly powerful. With it, Newton could not only explain the fall of an apple and the orbit of the moon, but he could precisely predict the elliptical paths of the planets that Kepler had so carefully observed. He could explain the existence of the tides, showing they were caused by the gentle, rhythmic stretching of the oceans by the moon's gravitational pull. He could even predict the path of comets as they swung in from the dark, cold edges of the solar system. For the first time, the universe seemed comprehensible, rational, and knowable. Humanity now possessed a vision of the cosmos as a magnificent and intricate machine, a great cosmic clockwork, wound up by a divine hand and left to run according to perfect, unchanging laws. There was a deep, spiritual comfort in this vision, a sense of order and predictability on the grandest of scales. Yet, for all its power, there was one question, one deep mystery at the heart of his theory that even Newton himself could not answer. He called it action at a distance. How, across the 93 million miles of cold, empty space, does the sun exert its pull on the Earth? How does it communicate its presence, its gravitational command, instantaneously? It was a philosophical puzzle that he chose to leave for others, a single, unexplained whisper in the heart of his majestic, silent, clockwork universe. It was a single, unexplained whisper in the heart of his majestic, silent, clockwork universe, a question that would hang in the quiet halls of science for more than 2 centuries. Newton's vision of gravity as an instantaneous, long-reaching force was so powerful, so successful at explaining the world, that this deep philosophical wrinkle was largely set aside. The cosmic machine ran beautifully, and for a time, that was enough. But the universe is patient, and it keeps its secrets in the smallest of details. As astronomical observations became more and more precise, another tiny crack began to appear in the flawless facade of the Newtonian model. It was found in the orbit of the planet closest to the Sun, Mercury. According to Newton's laws, the elliptical orbit of a planet should remain fixed in space, tracing the same path over and over again. But Mercury's orbit refused to behave. Very, very slowly, the entire ellipse was rotating, a gradual shift, a wobble known as precession. Most of this tiny wobble could be explained by the gravitational tugs of the other planets, like Venus and Jupiter. But when all the calculations were done, there was a small, stubborn discrepancy left over. A tiny deviation of just 43 arcseconds per century, a minuscule error that hinted that the story of gravity might not be complete. It was another anomaly, like the backward dance of the planets for the ancient Greeks, a persistent, quiet whisper that something deeper was at play. The clues to solving this mystery would not come from studying gravity itself, but from an entirely different realm of physics, the study of light, electricity, and magnetism. In the mid-1800s, a Scottish scientist named James Clerk Maxwell performed one of the greatest unifications in the history of science, weaving these 3 seemingly separate phenomena into a single, elegant theory of electromagnetism. And hidden within his beautiful equations was a startling prediction. He discovered that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field, and that these 2 fields could lock together, creating a self-propagating wave that travelled through space. When he calculated the speed of this wave, he arrived at a number that was already very familiar: 186,000 miles per second. It was the speed of light. Light, he realized, was an electromagnetic wave. But the most profound part of his discovery was that this speed, denoted by the letter c, appeared to be a fundamental constant of nature, a fixed value woven into the very fabric of reality. This led to a deeply strange and unsettling idea, later confirmed by the work of Albert Einstein in his theory of special relativity in 1905. The speed of light is not relative, it is absolute. No matter how fast you are moving towards a beam of light or away from it, you will always measure its speed to be exactly the same. This meant that the speed of light was a cosmic speed limit, the fastest that any information, any object, any influence could possibly travel from one point in the universe to another. And here, the beautiful clockwork of Newton's universe finally faced a problem it could not resolve. A conflict arose between two pillars of physics. Newton's gravity was a force that acted instantaneously, everywhere. If the sun were to suddenly vanish, Newton's equations implied that the Earth would, at that very same moment, fly off into space, its orbit instantly broken. But Einstein's special relativity declared that this was impossible. The information that the sun had disappeared could not travel faster than the speed of light. It would take 8.5 minutes for the last rays of sunlight to reach our eyes, and therefore it must take at least 8.5 minutes for the gravitational effect of the sun's disappearance to reach us as well. Gravity could not be instantaneous. The perfect Newtonian harmony was broken by a cosmic speed limit. The notion of a simple, pulling force acting at a distance was no longer tenable. The universe was not a great machine of gears and levers. It was something stranger, deeper, and infinitely more elegant, and it would take another decade of profound thought to uncover the true nature of this silent, all-pervading presence. The perfect Newtonian harmony was broken by a cosmic speed limit. The notion of a simple, pulling force acting at a distance was no longer tenable. The universe was not a great machine of gears and levers. It was something stranger, deeper, and infinitely more elegant, and it would take another decade of profound thought to uncover the true nature of this silent, all-pervading presence. The mind that would solve this puzzle was the same one that had first illuminated it, Albert Einstein. And the breakthrough came not from a complex calculation or a laboratory experiment, but from a moment of pure, imaginative insight, a sudden realization that he would later call his happiest thought. In the year 1907, while working at the patent office in Bern, Switzerland, he imagined a person falling from the roof of a house. He realized that as this person fell, they would not feel their own weight. If they were to let go of an object they were holding, it would float beside them, seemingly weightless. In that moment of freefall, the force of gravity would seem to disappear entirely. This simple, powerful image sparked a revolutionary idea. What if gravity, as a force, was an illusion? What if the experience of gravity was fundamentally indistinguishable from another, more familiar experience? The experience of acceleration. This was the seed of his principle of equivalence, the cornerstone of his new theory of gravity. To understand this profound thought, allow yourself to drift into an imaginary space. Picture yourself inside a small, sealed room, a kind of elevator, floating in the silent, empty void of deep space, far from any planet or star. You are perfectly weightless. If you push gently off one wall, you will float without effort to the other. Now, imagine that a great, invisible rope is attached to the top of your room and begins to pull it upwards, accelerating it smoothly and constantly. You would immediately feel a pressure on the soles of your feet. You would feel a sense of weight, a familiar downward pull. If you were to drop a small ball from your hand, it would not float. It would fall to the floor, because the floor is accelerating upwards to meet it. If you were to stand on a scale, it would register a weight. From your perspective, inside this windowless room, this experience would be completely and totally identical to the feeling of standing still on the surface of the Earth. There is no experiment you could perform, no measurement you could take, that could tell you whether you are at rest in a gravitational field or accelerating through empty space. The two states are, from a local perspective, perfectly equivalent. This simple, elegant idea has a profound consequence. If there is no difference between gravity and acceleration, then perhaps gravity is not a force that pulls you down. Perhaps, instead, it is a kind of acceleration. This turns Newton's universe on its head. We do not feel the Earth's gravity pulling on us. We feel the surface of the Earth constantly pushing up against us, preventing us from following our natural path through the cosmos, just as the floor of the accelerating elevator pushes up against the feet of its occupant. Now, let's return to that elevator, accelerating through the silent void of space. Imagine we shine a thin beam of light through a tiny hole in one wall. The beam travels across the room in a straight line. But because the room is accelerating upwards, by the time the light reaches the opposite wall, the room has moved. To you, inside, the light beam would appear to have followed a gentle, downward curve. Its path would be bent. And now comes the heart of the happiest thought. If acceleration can bend the path of light, and gravity is indistinguishable from acceleration, then gravity itself must also bend light. It must be able to alter the path of a sunbeam as it passes by a star, to change the course of light itself. This was an astonishing and radical prediction. Gravity was not a force that acted on mass. It was something that could influence the very path of light, something that could shape the geometry of space itself. This was an astonishing and radical prediction. Gravity was not a force that acted on mass. It was something that could influence the very path of light, something that could shape the geometry of space itself. But what is this space that can be shaped and bent? Einstein's earlier work on special relativity had already provided a clue, suggesting that space and time are not separate and absolute, but are instead deeply interwoven. We live our lives in a theatre of three spatial dimensions. We can move forward and backward, left and right, and up and down. But we are also, all of us, constantly moving in another, fourth dimension. The dimension of time. Every tick of the clock, every beat of the heart, is a small step forward along this temporal river. Einstein unified these four dimensions into a single, dynamic entity he called spacetime. Your journey through life is not just a path through space, from one location to another. It is a trajectory through the four-dimensional landscape of spacetime. This fabric of reality, this union of all places and all moments, became the new stage upon which the drama of the cosmos would play out. And it was this stage, this fabric, that Einstein realized was not passive and unchanging, but was active, flexible, and alive. To help your mind gently grasp this profound concept, imagine the fabric of spacetime as an immense, perfectly flat, and infinitely flexible sheet, like a cosmic trampoline stretched taut and level in every direction. This is what spacetime would be like in a completely empty universe, a perfect, featureless plane. Now, let us place a heavy bowling ball in the center of this sheet. The ball, representing our sun, with its great mass, sinks into the fabric, creating a deep, smooth, curved depression, a gravitational well. This is the first half of Einstein's revolutionary theory of general relativity, a concept captured in a beautifully simple phrase. Mass tells spacetime how to curve. Every object with mass creates a curvature in the fabric of spacetime around it. The more massive the object, the deeper and more pronounced the curve. Our Earth, being less massive than the Sun, would be like a small marble placed on the sheet, creating its own much gentler indentation. The Moon, a smaller pebble, would create a still smaller dimple within the curve made by the Earth. And you, lying here, your body with its own humble mass, creates a tiny, almost infinitesimal depression in the fabric of the universe, a subtle warping of the cosmos that is uniquely your own. The entire universe is a tapestry of these curves and wells, a dynamic, invisible landscape shaped by the presence of every star, every planet, every living being. Now, imagine we take another small marble, representing the Earth, and give it a gentle push sideways across the trampoline, not directly at the central bowling ball, but near its gravitational well. The marble does not travel in a straight line across the flat sheet. Instead, it is caught by the curve, and it begins to circle around the central depression, following the natural contour of the fabric. It is not being pulled by a mysterious, invisible string. There is no force reaching out from the bowling ball to grab it. The marble is simply following the straightest possible path it can through the curved surface. This natural path, this line of least resistance through a curved geometry, is called a geodesic. And this is the second, equally beautiful half of Einstein's theory. Space-time tells matter how to move. The Earth is not being pulled by the Sun's gravity. The Earth is simply continuing its journey in a straight line, but through a region of space-time that has been deeply curved by the Sun's immense presence. What we feel and interpret as the force of gravity is nothing more than the sensation of traveling along these natural curves in the four-dimensional fabric of the universe. An orbit is not a struggle. It is a surrender to the most effortless path. A falling apple is not being pulled to the ground. It is simply following its own geodesic in the space-time curved by the mass of our planet. The grand, mechanical clockwork of Newton was gone, replaced by a vision of the cosmos as a silent, graceful dance, a ballet of matter and geometry, where everything is simply and peacefully following the path of least resistance. The grand, mechanical clockwork of Newton was gone, replaced by a vision of the cosmos as a silent, graceful dance, a ballet of matter and geometry, where everything is simply and peacefully following the path of least resistance. This new perspective transforms our understanding of motion in the universe. The Earth, in its long and patient journey around the Sun, is not engaged in a constant struggle, forever pulled by an invisible tether. Instead, it is in a perfect state of cosmic freefall, coasting along the natural, effortless contours of space-time. To truly feel this, imagine the experience of an astronaut floating inside the International Space Station. They are not in a place where gravity has vanished. In fact, the Earth's gravitational influence at their altitude is nearly 90% as strong as it is on the surface. They feel weightless because they, and their station, are in a continuous state of falling, moving sideways so fast that they perpetually miss the Earth, tracing a perfect geodesic around our world. Their feeling of weightlessness is the true and uninhibited experience of following the curve, a feeling of pure, unimpeded motion through the geometry of the cosmos. Our planet shares in this same effortless state as it journeys around the Sun, and our Sun partakes in this same dance as it follows its own immense, 230 million-year orbit around the gravitational center of our Milky Way galaxy. The entire universe is in a state of serene, geometric motion. But perhaps the most beautiful and compelling evidence for this curved reality is not seen in the slow, patient orbits of planets, but in the path of light itself, as it travels across the immense distances between galaxies. As Einstein predicted, the curvature of space-time can bend the path of light. A sufficiently massive object, like an entire galaxy or a vast cluster of galaxies, can warp the space-time around it so profoundly that it acts like a cosmic lens, a piece of celestial glass ground by gravity itself. Imagine the light from a very distant galaxy, a faint and ancient whisper from the early universe, embarking on a journey of billions of years toward us. If, along its path, this light happens to pass through the deep gravitational well created by another, closer galaxy, its path will be bent, its trajectory altered by the curved landscape. To us, here on Earth, looking back along the path of these redirected light rays, the distant galaxy will appear distorted, magnified, and sometimes even multiplied. Through our greatest telescopes, we can see these breathtaking celestial illusions, direct photographs of the invisible geometry of the universe. Sometimes, the distant galaxy is smeared into a luminous, ghostly arc, its shape stretched and warped by the cosmic lens. In other, more perfectly aligned cases, we might see what is known as an Einstein cross, where the light from a single, distant, brilliant object like a quasar is split by the lensing galaxy into 4 distinct images. A perfect, glowing cloverleaf arranged around the central mass, and in the rarest and most perfect alignment of all, when the distant galaxy, the lensing galaxy, and the Earth are all in a perfect straight line, the light of the distant object is stretched into a complete and shimmering halo of light, a perfect circle of ancient starlight known as an Einstein ring. These images are among the most profound and beautiful in all of science, for they are not just pictures of distant, shining objects. They are pictures of gravity itself. We are seeing the unseen. We are witnessing the invisible shape of the space-time fabric, revealed to us by the path of light that has traveled through it. The dark, empty spaces between the stars are not empty at all, but are filled with this dynamic, curving geometry, a landscape of hills and valleys that guides and shapes everything that moves through it. And as we gaze upon these ghostly rings and celestial crosses, we are reminded that our perception of the universe is always a story told by light, a story whose path is shaped by the silent, ever-present curvature of space-time. As we gaze upon these ghostly rings and celestial crosses, we are reminded that our perception of the universe is always a story told by light, a story whose path is shaped by the silent, ever-present curvature of space-time. The curve of space-time around a galaxy can bend light, but what if a curve could be so deep, so extreme, that it could capture light entirely? What if an object could become so dense that the landscape around it becomes a well with no bottom, a pit from which even the fastest thing in the universe cannot climb out? This is the conceptual gateway to one of the most mysterious and awe-inspiring objects in the cosmos: a black hole. The story of a black hole begins with the death of a truly colossal star, a star born with dozens of times the mass of our own sun. For millions of years, this luminous giant lives in a state of perfect, violent equilibrium. Deep within its core, the crushing force of its own immense gravity tries to collapse it, but it is held at bay by the ferocious, outward pressure of nuclear fusion, the same process that makes the star shine. It is a lifelong battle between collapse and radiance, between gravity and light. But this battle cannot last forever. Eventually, the star exhausts the fuel in its core. The nuclear fires begin to die, the outward pressure fades, and gravity, patient and relentless, finally wins. In less than a second, the star's core collapses in upon itself in a catastrophic implosion. The outer layers of the star are blasted away in a supernova, one of the most brilliant and violent events in the universe, for a few brief weeks outshining an entire galaxy of 100 billion stars. But it is in the darkness that follows this flash of light that the true wonder occurs. Left behind is the crushed, collapsed remnant of the star's core. To understand what happens next, we must consider a concept known as escape velocity. Here on Earth, if you want to launch a rocket into space so that it never falls back down, you must accelerate it to a speed of about 7 miles per second, or 25,000 miles per hour. This is Earth's escape velocity. If you were on the surface of a more massive planet, like Jupiter, the escape velocity would be much higher, because its gravity is stronger. Now, imagine the collapsed core of our dead star. It might contain the mass of 3 or 4 of our suns, but it has been crushed down into a sphere only a few miles across. The density is almost unimaginable, and the gravity at its surface is titanic. The escape velocity from this remnant would be hundreds of millions of miles per hour. As the core continues to collapse under its own weight, shrinking ever smaller, the escape velocity at its surface continues to climb, getting ever closer to the ultimate cosmic speed limit. And then, it crosses a threshold of no return. The collapse continues until the escape velocity at a certain boundary surpasses the speed of light itself. Since nothing, absolutely nothing, can travel faster than light, this means that nothing that crosses this boundary can ever escape. Not a spaceship, not a particle, not even a beam of light. This boundary is not a physical surface you could touch. It is a silent, one-way door in space-time. It is the event horizon. It is a waterfall in the river of the cosmos, and everything that flows over its edge is lost from the visible universe forever. And what lies within? According to our current understanding, at the very heart of the black hole, the collapse continues until all of that immense mass is crushed into a single point of zero size and infinite density, a place called the singularity. Here, the curvature of space-time becomes infinite. The landscape is no longer a gentle well, but an endless abyss. At the singularity, space and time as we know them dissolve, and all the known laws of physics, including Einstein's own beautiful theory, break down completely. It is the ultimate mystery, a point of infinite silence where the story of the universe as we can tell it simply stops. It is gravity in its most absolute and final form, a quiet, dark well in the fabric of reality. It is the ultimate mystery, a point of infinite silence where the story of the universe, as we can tell it, simply stops. It is gravity in its most absolute and final form, a quiet, dark well in the fabric of reality. And just as this extreme curvature distorts the path of light and the very shape of space, it also has a profound and bewildering effect on the flow of time. One of the most beautiful and strange predictions of Einstein's theory is that time is not a universal clock, ticking at the same steady rate for everyone, everywhere. Instead, time is fluid, malleable, and its pace is intimately connected to the strength of gravity. This is the phenomenon of gravitational time dilation. The deeper you are within a gravitational well, the slower the river of time flows. Even here, on the surface of the Earth, Time passes ever so slightly more slowly than it does for a satellite in high orbit, where gravity's embrace is a little less firm. The difference is minuscule, a matter of microseconds per day, but it is real, a subtle whisper of a much grander cosmic truth. And nowhere is this truth more pronounced than near the edge of a black hole, where the river of time slows to a deep and silent crawl. To explore this, let us embark on a gentle, imaginary journey. Picture yourself in a small, sturdy spaceship, drifting in the quiet darkness of space. In the distance, you see your destination, a solitary black hole, a perfect circle of absolute blackness outlined against the glittering tapestry of the stars. With you is a companion ship, which will remain here at a safe distance, a silent observer to your voyage. As you begin your journey inward, gently firing your engines to start your descent into the gravitational well, everything inside your craft feels perfectly normal. Your clock on the wall ticks with a familiar, steady rhythm, 1 second at a time. Your heart beats in its usual peaceful cadence. You feel no sense of hurry, no strange distortion, only the growing darkness ahead. But for your companion, watching you from afar through a powerful telescope, a very different story unfolds. As your ship ventures deeper into the curve of space-time, they would see the light from your ship begin to shift. The intense gravity would stretch the light waves, shifting them towards the red end of the spectrum, causing your ship to appear dimmer and redder. And stranger still, they would see your clock begin to run slow. Your every movement would appear to them to be happening in a kind of celestial slow motion. As you get closer and closer to the precipice, to the silent boundary of the event horizon, this effect would become extreme. From your companion's perspective, your ship's progress would seem to grind to a halt. The seconds of your clock would stretch into minutes, then hours, then centuries. You would appear to be frozen in time, a faint, red, ghostly image plastered for all eternity on the edge of the abyss, never quite crossing over. They would witness your journey take an infinite amount of their time. And yet, for you, inside your ship, time would continue its normal, peaceful flow. You would feel no pause, no hesitation. You would simply drift across the event horizon in a finite and perhaps even brief amount of time, slipping from the visible universe into the unknown. This is the profound paradox of the black hole. Both realities, the observers and the travelers, are true in their own frame of reference. Time is personal, and as you fall, you would encounter another of gravity's strange effects. If the black hole were relatively small, the mass of a single dead star, the tidal forces would be immense. The gravitational pull on your feet, being slightly closer to the singularity, would be exponentially stronger than the pull on your head. These tidal forces would stretch your ship, and you, vertically, while squeezing you horizontally, a process with the unsettling name of spaghettification, a final, complete dissolution into a stream of atoms before you even reach the center. Time, in the end, is a river, and its current depends entirely on where you are flowing in the vast curved landscape of the cosmos. Time, in the end, is a river, and its current depends entirely on where you are flowing in the vast, curved landscape of the cosmos. At the edge of a black hole, from our distant perspective, that river appears to freeze, creating an image of eternal, silent stillness. For a long time, our only way of knowing the universe was through light, through these silent images that crossed the void to reach our telescopes. The cosmos was a beautiful but silent movie. But what if the greatest events in the universe were not silent at all? What if the very fabric of space-time could ring like a drum, carrying the sound of cosmic collisions across the eons? Einstein's theory of general relativity predicted exactly this. He realized that if space-time is a flexible, dynamic fabric, then certain violent events could create ripples in its curvature, vibrations that would travel outwards in all directions. These are not waves that travel through space, like sound waves traveling through air. They are waves of space itself. They are gravitational waves. Imagine again the cosmic trampoline. If a massive object on it were to suddenly move or change shape, it would send waves of energy propagating across the sheet. In the same way, when massive objects in our universe accelerate in violent ways, they radiate away energy in the form of these subtle, propagating shivers in the geometry of reality. The sources of these waves are the most energetic and cataclysmic events the universe has to offer. Picture two black holes, born from the deaths of ancient, massive stars, locked in a gravitational embrace. For millions of years, they orbit each other in a slow, patient spiral. As they draw closer and closer, they move faster and faster, whipping around each other hundreds of times per second in the final moments of their dance. In doing so, they violently churn the space-time around them, sending out powerful, spiraling waves of gravitational energy. In the final fraction of a second, they merge into a single, larger black hole, a collision of such unimaginable power that it converts several times the mass of our Sun into pure gravitational energy, released in a single, brilliant burst that shakes the entire cosmos. Other events, like the collision of two neutron stars, the incredibly dense, city-sized remnants of smaller supernovae, can also send out these cosmic tremors, as can the asymmetrical explosion of a single, dying star. These are the sounds of creation and destruction, the deep, resonant hum of the universe in motion. For decades, these waves were only a beautiful prediction, a ghost in the mathematics of Einstein's theory. They were so astonishingly faint that he himself doubted we would ever be able to detect them. By the time a gravitational wave from a distant galaxy reaches the Earth, the ripple it creates in space-time is thousands of times smaller than the nucleus of a single atom. Detecting such a subtle disturbance is one of the greatest technological challenges ever undertaken by humanity. But we built an ear to listen. It is called LIGO, the Laser Interferometer Gravitational Wave Observatory. It consists of two identical facilities, thousands of miles apart, each one an immense L shape with two arms that are 2.5 miles long. Inside each arm, a powerful laser is bounced back and forth between perfectly polished mirrors. When space-time is perfectly calm and flat, the two laser beams cancel each other out perfectly. But if a gravitational wave passes through, it will momentarily stretch one arm of the detector while squeezing the other, changing their lengths by an infinitesimal amount. This tiny change is enough to knock the laser beams out of alignment, creating a flicker of light, a signal of a passing cosmic tremor. On September 14th, 2015, it finally happened. A signal arrived, a gentle rising chirp that lasted for less than half a second. It was the sound of two black holes, about 1.3 billion light-years away, finally merging into one. For the first time, we did not see a cosmic event. We heard it. We felt the vibration of space-time itself. The silent movie of the universe had just become a symphony, and we had finally learned how to listen. The silent movie of the universe had just become a symphony, and we had finally learned how to listen. And while the sounds we have heard so far are often the sounds of cosmic endings, the final, violent merger of two black holes, the force that drives these events is also, on a much grander and more patient timescale, the ultimate engine of creation. The story of gravity is not just one of collapse. It is the story of how the universe built itself from a formless, quiet beginning. Let your mind drift back in time, back through the long, dark eons to the dawn of the cosmos. In the aftermath of the Big Bang, the universe was an almost perfectly smooth, uniform place, a vast, expanding fog of hydrogen and helium gas, shimmering with the faint afterglow of its own creation. There were no stars to light the darkness, no planets, no galaxies, only this thin, featureless mist. But it was not perfectly uniform. There were tiny, almost infinitesimal fluctuations in its density, regions where the fog was just a fraction of a percent denser than the regions around it. And in these minuscule imperfections, gravity found its first foothold. Patiently, relentlessly, over the course of 100 million years, gravity began its slow and gentle work. In the places where the gas was ever so slightly denser, the gravitational pull was ever so slightly stronger. This stronger pull began to draw in more gas from the surrounding regions, making the dense patch even denser, and its gravitational pull even stronger still. It was a process of quiet, runaway accumulation, a cosmic gathering that unfolded in the immense silence of the early universe. As these clouds of gas grew more massive, They began to collapse under the weight of their own gravity, spinning faster and faster, heating up as the pressure mounted in their cores, until, one by one, the first stars ignited, flooding the primordial darkness with the first light. This same gentle, persistent principle of gravitational gathering then began to play out on a much larger scale. These first, brilliant blue stars were not born alone, but in great clusters. These clusters, along with the vast reservoirs of gas that surrounded them, began to pull on each other across the growing distances of the expanding universe. They began to drift together, merging and growing over hundreds of millions of years, forming the first small, irregular galaxies. These galaxies, in turn, continued their slow, gravitational dance, colliding and merging in a great cosmic ballet that has continued for over 13 billion years, building the grand, majestic spiral and elliptical galaxies, the great cities of stars like our own Milky Way, that we see today. But as astronomers began to study these galaxies, they discovered a deep and profound mystery. When they measured the speeds of the stars orbiting in the outer regions of a galaxy, they found that the stars were moving far too quickly. Based on all the visible matter they could see all the stars, the gas, the dust, there simply was not enough gravitational pull to hold these fast-moving stars in their orbits. The galaxies should have flown apart, their outer stars flung off into the darkness of intergalactic space. It seemed that the universe contained a hidden substance, an invisible form of matter that does not shine or reflect light, but which possesses gravity. This mysterious presence was given the name dark matter. We now believe that every galaxy, including our own, is embedded in a vast, spherical halo of this dark matter, an invisible scaffolding that provides the extra gravitational grip necessary to hold the galaxy together. This unseen substance, we think, makes up about 85% of all the matter in the universe, an invisible ocean in which the luminous islands of the galaxies reside. And it is the gravity of this dark matter that has sculpted the universe on the very largest of scales. When we map the positions of millions of galaxies in the sky, we find that they are not scattered randomly like dust. Instead, they are arranged in an immense and beautiful pattern, a vast, interconnected structure known as the cosmic web. We see long, glowing filaments of galaxies stretching for hundreds of millions of light years, and great, dense superclusters where these filaments intersect, the bustling metropolises of the cosmos. And surrounding these structures are immense, dark, and startlingly empty regions called cosmic voids. This entire, breathtaking structure is the result of gravity, acting primarily on the unseen dark matter, pulling it into these filaments and clusters over the entire age of the universe, and the visible matter, the shining galaxies, have simply followed along, tracing the shape of this invisible cosmic architecture. Gravity, it seems, is the universe's silent, patient artist, the sculptor of stars and the weaver of the cosmic web. Gravity, it seems, is the universe's silent, patient artist, the sculptor of stars and the weaver of the cosmic web. For most of the 20th century, this was the story we told ourselves about the ultimate fate of the universe. The cosmos was born in a fiery expansion, the Big Bang. But since that moment, the relentless, inward pull of gravity from all the matter and dark matter has been working to slow that expansion down. The great question was simply, is there enough gravity to eventually stop the expansion and cause the universe to recollapse in a big crunch? Or would the expansion slow down forever, leading to a cold, dark, and empty future? For decades, astronomers sought to measure the rate of this cosmic deceleration to determine which fate awaited us. But the universe, it turned out, had a far stranger and more surprising story to tell. To understand this story, we must first picture the expanding cosmos. The discovery, made by Edwin Hubble in the 1920s, that the universe is expanding, transformed our view of reality. He observed that distant galaxies are all moving away from us, and the farther away a galaxy is, the faster it appears to be receding. This is not because we are at the center of some great explosion, but because the fabric of space-time itself is stretching. A simple way to visualize this is to imagine a loaf of raisin bread rising in an oven. As the dough expands, every raisin moves away from every other raisin. From the perspective of any single raisin, all the others appear to be rushing away, and the ones farthest away will appear to be moving the fastest. For decades, the central quest of cosmology was to measure the precise history of this expansion. The key was to find a standard candle, a type of celestial object with a known, uniform brightness, which could be used to measure distances to the farthest reaches of the universe with incredible accuracy. In the 1990s, astronomers found just such a candle in a rare and brilliant type of stellar explosion called a Type 1, a supernova. These supernovae are all thought to explode with almost exactly the same intrinsic brightness, meaning that by measuring how dim they appear to us, astronomers can calculate how far away they are. Two independent teams of scientists set out on a grand project to find these distant supernovae and use them to measure how much the cosmic expansion had slowed over the past several billion years. They gathered their data, made their calculations, and when they looked at the results, they found something that no one had ever expected, something that seemed impossible. The expansion of the universe was not slowing down. It was speeding up. The universe is accelerating. This discovery was so profound, so utterly world-changing, that it was awarded the Nobel Prize in Physics in 2011. It meant that the universe must be filled with a mysterious, invisible influence, a kind of cosmic anti-gravity that is pushing space-time apart. This unknown presence was given a suitably mysterious name: dark energy. Unlike gravity, which is associated with matter and gets weaker as matter spreads out, dark energy seems to be a property of space itself, a kind of energy inherent in the vacuum. As the universe expands, new space is created, and with it, more of this dark energy, causing the expansion to accelerate even faster. It is a gentle, persistent push that only becomes dominant on the very largest of cosmic scales. Within a galaxy, gravity is still by far the stronger influence, holding our solar system and our stars together in a tight, familiar embrace. But in the vast, empty gulfs between the galaxies, the cumulative push of dark energy wins out, driving them away from each other at an ever-increasing speed. Curiously, this idea had a ghostly echo from the past. When Albert Einstein first formulated his theory of gravity, his equations predicted a universe that was either expanding or contracting. Believing, as everyone did at the time, that the universe was static and eternal, he added a term to his equations to hold it still, a kind of cosmic repulsion he called the cosmological constant. When Hubble discovered the expansion, Einstein discarded the idea, calling it his biggest blunder. And yet, a century later, it seems he may have been right for the wrong reason. This cosmological constant, this energy of empty space, is now our leading model for what dark energy might be. And so we find ourselves living in a cosmos defined by a grand and delicate tension, a cosmic tug-of-war between the familiar, comforting pull of gravity that gathers matter into stars and worlds, and the strange, unknown push of dark energy that is slowly, but inexorably, driving the universe apart. And so we find ourselves living in a cosmos defined by a grand and delicate tension, a cosmic tug-of-war between the familiar, comforting pull of gravity that gathers matter into stars and worlds, and the strange, unknown push of dark energy that is slowly, but inexorably, driving the universe apart. This grand narrative, a story of curved space-time, dark matter, and accelerating expansion, is our best and most beautiful description of the universe on the largest of scales. But the journey into the story of gravity now leads us to one final, profound frontier, a place where our most successful theories fail us, and the cosmos draws a veil over its deepest secrets. We arrive at the strange and wonderful conflict between the two great pillars of modern physics, the two most successful descriptions of reality ever conceived by the human mind. The first pillar is Einstein's general theory of relativity, the very story we have been exploring. It is the theory of the very large. Its language is the language of geometry, of smooth, flowing curves in the fabric of space-time. It describes the graceful orbits of planets, the bending of starlight, the slow dance of galaxies, and the silent, deep wells of black holes. It is a theory of breathtaking elegance and macroscopic power, a story of the cosmic landscape, The second pillar is the theory of quantum mechanics. It is the theory of the very small. It describes the world of atoms and the particles within them, the realm of electrons, photons, and quarks. And this world is utterly unlike the smooth, predictable cosmos of Einstein. The language of quantum mechanics is the language of probability and uncertainty, of discrete, indivisible packets of energy called quanta. It is a world where a particle can be in many places at once until it is observed, where emptiness is a fizzing, bubbling foam of virtual particles flashing in and out of existence. It is a bizarre, counterintuitive, and yet spectacularly successful theory, forming the foundation of almost all modern technology, from lasers to computers to nuclear energy. For nearly a century, these two great theories have coexisted, each reigning supreme in its own domain. General relativity governs the stars. Quantum mechanics governs the atoms that make up those stars. But there are places in the universe where these two domains are forced to meet, places where the very large becomes the very small. And it is here that our understanding of physics breaks down completely. Imagine the singularity at the heart of a black hole, a place where the mass of an entire star is crushed down to a point of infinite density. This is a place of immense gravity, the realm of general relativity, but it is also a place of infinitesimal size, the realm of quantum mechanics. Here, the two great pillars of our knowledge collide, and their equations produce nonsensical answers, infinities that tell us our theories are incomplete. The same is true for the very first moment of the universe, the instant of the Big Bang, when the entire observable cosmos was packed into a space smaller than an atom. To understand these ultimate origins and ends, we need a deeper theory, a single framework that can unite gravity with the quantum world. We need a theory of quantum gravity. The search for this theory is the greatest unsolved problem in physics today. We have promising, beautiful ideas, but as yet no definitive answers. One leading candidate is called string theory, which proposes that the fundamental constituents of reality are not point-like particles, but tiny, one-dimensional, vibrating strings. In this vision, every particle we see an electron, a photon, a quark, is just a different note played by these cosmic strings. Gravity, in this beautiful musical analogy, is simply one of the notes in the grand, universal symphony. Another approach is called loop quantum gravity, which suggests that the fabric of spacetime itself is not smooth and continuous, but is woven from incredibly tiny, discrete, indivisible loops. In this view, space is not a sheet, but a tapestry, and there is a smallest possible size, a fundamental pixel of reality known as the Planck length. And so, our story of gravity, which began with the simple feeling of a blanket, has led us here to the very edge of human knowledge, to the final veil of mystery. And so our story of gravity, which began with the simple feeling of a blanket, has led us here to the very edge of human knowledge, to the final veil of mystery. The quest for a unified theory of quantum gravity is a journey into the deepest and most abstract questions we can ask about the nature of reality. But as our minds return from these distant frontiers, we find that the connection between gravity and the fabric of existence is not merely a subject for theoretical physics. It has subtle, real, and deeply personal implications for each of us, particularly in our relationship with the most intimate and mysterious dimension of all, time. We have already drifted through the strange idea of gravitational time dilation, the prediction from Einstein's theory that the stronger the gravity, the slower time flows. This is not a speculative or metaphorical concept. It is a measurable and essential feature of the universe we inhabit, a truth that quietly affects our lives every single day, whether we are aware of it or not. The most profound and practical example of this is woven into the technology that many of us now take for granted, the Global Positioning System, or GPS. This remarkable system relies on a constellation of dozens of satellites orbiting high above the Earth, each one carrying an incredibly precise atomic clock. These satellites are in a region where the Earth's gravity is significantly weaker than it is down here on the surface. Because of this, Einstein's theory predicts that the clocks on board those satellites should tick slightly faster than our clocks on the ground. At the same time, because the satellites are moving at high speeds, his theory of special relativity predicts their clocks should tick slightly slower. When both of these effects are calculated, the dominant one is gravity's. The result is that the satellite clocks gain, on average, about 38 microseconds every single day compared to clocks on the ground. A microsecond is just 1/1,000,000th of a second, a duration so fleeting as to seem completely insignificant. And yet, if the engineers who designed the GPS system did not constantly account for this tiny relativistic difference, this subtle stretching and shrinking of time itself, the system would fail catastrophically. The positioning errors would accumulate at a rate of more than 6 miles every single day, rendering the entire network useless within minutes. Every time you use a map on your phone to find your way, you are relying on the practical truth of Einstein's profound insight. The flow of time is not absolute, but is tethered to the local curvature of spacetime. This idea can be made even more personal through a famous thought experiment called the twin paradox. Imagine two identical twins. One stays on Earth, while the other embarks on a long journey into space aboard a rocket that travels close to the speed of light. When the traveling twin returns to Earth, they will find that they have aged less than the twin who remained at home. Their journey through spacetime has altered their journey through time. While speed is the dominant factor in this famous example, gravity plays its own subtle part in our own lives. A person who lives their entire life at sea level, deeper in Earth's gravitational well, will age ever so slightly more slowly than a person who lives their life on a high mountaintop. The difference is unimaginably small, far too tiny to ever notice, but it is real. And this leads to a wonderfully contemplative and peaceful realization. Your experience of time is uniquely your own. It is a personal river, its flow shaped by your own specific journey through the cosmos, by the gravitational embrace of the world you inhabit. There is no single, universal clock ticking for everyone. There is only your river of time and my river of time, each one flowing at its own gentle, unique pace, its current guided by the silent, invisible landscape of space-time. There is no single, universal clock ticking for everyone. There is only your river of time and my river of time, each one flowing at its own gentle, unique pace, its current guided by the silent, invisible landscape of space-time. And just as gravity shapes our personal, temporal journey through the cosmos, it appears to have played a profound and decisive role in preparing the way for that journey to even begin. The story of gravity is not only the story of stars and planets, but also the story of the intricate and unlikely path that led to the emergence of life itself. To appreciate this deep connection, we must first ask a simple question. Where did the ingredients of life come from? Where did the atoms that make up your body, the air you breathe, the water that sustains you, originate? The very beginning of the universe, in the aftermath of the Big Bang, created only the very lightest and simplest of elements, almost entirely hydrogen and helium, with a trace of lithium. There was no carbon, no oxygen, no nitrogen, no iron, none of the essential elements that form the basis of biology as we know it. For these atoms to exist, they had to be forged. And so they were, in the only places in the early universe hot enough and dense enough to do so. The hearts of the first great stars. Within these stellar furnaces, under the immense pressure of gravity, hydrogen and helium atoms were fused together to create heavier elements in a process called stellar nucleosynthesis. Carbon, the backbone of all life, was forged. Oxygen, the element that fills your lungs with every breath, was created. All the elements of the periodic table, up to and including iron, were built, layer by layer, in the cores of these massive, brilliant stars over millions of years. But for these precious, life-giving elements to be of any use to the rest of the universe, they had to be released from the stars that made them. And so, the stars had to die. In their final, spectacular moments, the most massive stars collapse under their own gravity, and then rebound in a titanic supernova explosion, scattering the elemental treasures they spent their entire lives creating far out into the darkness of interstellar space. This stardust, this beautiful and enriching cosmic debris, then mingled with the primordial clouds of hydrogen and helium, seeding them with the raw materials needed for the next generation of stars and for the rocky planets that would form around them. It is one of the most poetic truths in all of science. You, and every living thing, are made of the ashes of long-dead stars. The elements for life were now present, scattered throughout the nebula from which our solar system was born. But our young Earth, forming close to the Sun, was likely a hot, dry, and barren world. So how did it receive the two most crucial ingredients for life to begin? Water, and the complex organic molecules that water could bring to life. The answer, it seems, came from the cold, dark, outer reaches of our solar system, and it was delivered by gravity. In the early days, our solar system was a much more chaotic and crowded place than it is today. It was filled with countless comets and asteroids, the leftover building materials from the formation of the planets. Comets, in particular, are like cosmic time capsules, dirty snowballs made of water ice and frozen gases, all mixed with complex, carbon-rich organic molecules. For hundreds of millions of years, during a period known as the Late Heavy Bombardment, the inner solar system was pelted by these objects. And the great celestial shepherd orchestrating this delivery was gravity itself. The immense gravitational fields of the giant outer planets, Jupiter and Saturn, acted like a cosmic slingshot, their powerful influence disrupting the orbits of these distant comets and asteroids, flinging them inwards on paths that would cross that of the young Earth. Over millions of years, our world was showered with these life-giving messengers, a celestial rain that delivered the water that would fill our oceans, and the very molecular building blocks, the amino acids and nucleic acids, that would eventually combine in those warm, sunlit waters to spark the first stirrings of life. Gravity, then, was not merely a passive stage for life's emergence. It was the cosmic courier, the patient, guiding hand that gathered the stardust and then delivered it, carrying the potential for life across the void and gently placing it into the cradle of a waiting world. Gravity was the cosmic courier, the patient, guiding hand that gathered the stardust and then delivered it, carrying the potential for life across the void and gently placing it into the cradle of a waiting world. And as life awoke and evolved within that cradle, it developed an intimate and profound relationship with this constant, nurturing presence. This relationship is not merely philosophical, it is written into the very fabric of our biology, into the silent, hidden machinery of our own senses. Deep within your inner ear, shielded by the bones of your skull, lies an intricate and beautiful structure, a marvel of evolutionary engineering called the vestibular system. This is your body's personal gravity detector. It is a labyrinth of tiny, fluid-filled canals that sense rotation, and it contains special organs that sense linear motion and, most importantly, the ever-present pull of gravity. Within these organs are microscopic crystals, like tiny, precious stones, called otoliths, that rest upon a bed of exquisitely sensitive hair-like cells. As you tilt your head, or as your body moves, these tiny crystals shift and slide, bending the hairs beneath them. This sends a constant stream of signals to your brain, a quiet, continuous whisper that tells you which way is down. This is the source of your sense of balance, your innate and immediate understanding of your own orientation in the world. It is a silent sense, operating so flawlessly and so constantly that we rarely, if ever, notice it. And yet it forms the fundamental foundation for every physical action we take. This deep, biological sense of down has echoes that resonate through our entire psychological experience. The constancy and reliability of gravity provide us with a profound, unspoken sense of comfort and security. Think of the language we use to describe a state of well-being. We speak of being grounded, of having our feet on the ground, of feeling stable and centered. These are not just metaphors. They are phrases born from a deep physical truth. Our minds and our emotional states are intimately tied to the predictable, physical reality that gravity provides. The simple, unwavering certainty that the floor will support you, that a cup let go will fall, that the world has a dependable up and down, creates a subconscious baseline of order and safety in our lives. It is the one constant in a world of perpetual change, a quiet, reassuring presence that holds our world and our minds together. It is the anchor that allows us to feel at home. To truly appreciate this silent gift, we can imagine the experience of those who have temporarily left it behind. Astronauts living in the microgravity of space. In the absence of this constant directional cue, the brain can become deeply disoriented. The vestibular system sends confusing signals, leading to a condition known as space adaptation syndrome, a kind of celestial motion sickness, as the mind struggles to recalibrate to a world with no down. Astronauts describe the strange, and sometimes unsettling, experience of having no anchor, of the floor and the ceiling being interchangeable, of the constant, conscious effort required to keep track of objects that will not stay put. Their experience reveals just how deeply we rely on gravity, not just for our physical balance, but for our mental and emotional equilibrium as well. It is an unsung, unnoticed source of peace. We so often think of letting go as an act of will, but it is gravity that makes this possible. The ability to rest, to relax your muscles, to surrender the weight of your body to your bed at the end of the day, is an act of trust in this fundamental force. You can let go because you know you will be held. Gravity is more than a physical law. It is the silent, constant reassurance of home, the gentle pressure that holds us close to the world and allows our minds the peace to wander, to reflect, and ultimately, to dream. Gravity is more than a physical law. It is the silent, constant reassurance of home, the gentle pressure that holds us close to the world and allows our minds the peace to wander, to reflect, and ultimately, to dream. To truly feel the depth of our gratitude for this silent, foundational anchor, let us embark on one final, gentle thought experiment together. Let us imagine, just for a few moments, a world without it. Let us, in our minds, gently switch off this fundamental force and watch what unfolds in the quiet that follows. In the first instant, the feeling of weight would vanish. The comforting pressure of your head on the pillow, the gentle heaviness of your blanket, all would be gone. You would begin to drift, unmoored, within your room. But you would not be alone. The pillow, the blanket, the bed itself, every object not bolted down would also begin to float, suspended in a sudden, silent chaos. The very air you breathe, no longer held captive by the Earth's embrace, would begin to expand outwards, its molecules dispersing into the cold, empty void of space. Outside, this gentle unraveling would become a catastrophe. The great oceans would lose their cohesion, their waters lifting from their beds and separating into a vast, drifting sphere of countless droplets. The mountains, no longer bound by the immense gravitational pressure that holds them together, would begin to crumble and fly apart. The entire planet, our beautiful solid Earth, would cease to be a sphere. Its molten core, its rocky mantle, and its fragile crust, all beginning to separate and drift away, a world dissolving back into a cloud of cosmic dust. Looking up into the sky of this disintegrating world, you would see the moon, its long, faithful orbit instantly broken, now sailing away on a straight, lonely path into the darkness. Our sun, too, would feel this sudden release. The immense gravitational pressure that contains its furious nuclear core would vanish, and this sudden lack of containment would cause it to erupt in a single, final, and catastrophic explosion, its substance blasted out into the solar system. And even if it did not explode, the planets that once danced around it would now be gone, each one flung out on its own tangential trajectory, becoming cold rogue worlds wandering the interstellar darkness. But the consequences of a gravity-free universe are deeper still, for such a universe would never have been born in the first place. The sun would never have formed, because the primordial cloud of gas and dust from which it was born would never have felt the gentle, inward pull required to coalesce, to collapse, and to ignite. The planets, including our Earth, would never have gathered themselves from the dust and pebbles of the early solar system. Zooming out to the grandest of scales, the entire cosmic story would be erased. The early universe, that nearly uniform fog of hydrogen and helium, would have simply continued expanding, thinning out, and cooling down forever. Without gravity, there would be no force to gather matter together, no seed for structure to grow. The great, glittering galaxies would never have formed. The cosmic web, with its beautiful filaments and clusters, would never have been woven. The universe would be a cold, dark, and eternally featureless place, a thin and silent soup of primordial gas. And in such a universe, there would be no stars to forge the heavy elements. There would be no carbon, no oxygen, no iron. There would be no rocky planets to provide a stable home. There would be no atmospheres, no oceans. The story of life, a story that requires structure, stability, and complex chemistry, would have been impossible from the very beginning. And so, we gently let this vision of a formless void dissolve, and we return our awareness to the present moment, to the quiet, familiar reality of our world, held together by this invisible, indispensable force. We see now that gravity is not a cage, but a cradle. It is not a force of limitation, but the fundamental principle of connection, of order, and of creation, the silent architect that makes a universe of beauty and being possible. We see now that gravity is not a cage, but a cradle. It is not a force of limitation, but the fundamental principle of connection, of order, and of creation, the silent architect that makes a universe of beauty and being possible. And so we return from that formless, imagined void, back to the gentle, familiar insistence of the world as it is, back to the quiet of your room, back to the comforting weight of your own body at rest. Our long journey together is coming to a close, a journey that began with the simplest of feelings and has carried us to the very edge of space, time, and understanding. We began here, in the intimate darkness, feeling gravity not as a law of physics, but as a personal embrace, the weight of a blanket, the surrender of your body to the bed. We discovered it as the silent architect of the living world, the force that taught the trees which way to grow and shape the very bones and blood that give you life. We travelled back in time to listen to the whispers from the ancient sky, to see the universe through the eyes of Aristotle, a cosmos of natural places and perfect spheres, a story born of a human need for order and a central place to call home. We felt the courage of Galileo as he let go of ancient dogma to trust what his own eyes could see, unifying the heavens and the earth into a single, knowable reality. We rested in the beautiful, clockwork universe of Isaac Newton, a cosmos of perfect, predictable laws, where the same force that pulls an apple to the ground also holds the moon in its timeless, celestial dance. Then, with Einstein as our guide, we took a leap into a much stranger and more wonderful reality, leaving behind the idea of a simple pull for the breathtaking vision of a flexible, four-dimensional space-time. We imagined the universe as a great, dynamic landscape, and we saw that gravity was nothing but the shape of that landscape, a curvature created by the presence of matter and energy itself. We learned that to be in orbit is simply to follow the most natural, effortless path along these cosmic contours. Our journey took us into the deepest wells in that landscape, to the silent, one-way doors of black holes, where the flow of time itself slows to a crawl. And we learned to listen, to hear the faint cosmic whispers of gravitational waves, the sound of colliding worlds, shaking the very fabric of reality. We zoomed out to see gravity as the grand cosmic sculptor, the patient artist that gathered the dust of dead stars to build new suns, new worlds, and the vast, luminous tapestry of the cosmic web. And finally, we brought this immense story back home, back to the deeply personal, feeling the way gravity shapes our own unique river of time and provides the constant, psychological anchor that gives us our sense of peace, of place, and of belonging. The story of gravity, in the end, is the story of connection. It is the universal thread that weaves the entire cosmos, from the smallest particle to the largest supercluster of galaxies, into a single, coherent whole. It is at once a force of unimaginable power, capable of crushing a star into nothingness, and a force of the utmost gentleness, the soft pressure that holds you securely as you prepare to sleep. As you finally let go of the day, as your thoughts begin to soften and drift, feel that gentle, constant presence one last time. It is the embrace of the earth, a world born of stardust. This earth is held in a cosmic dance by the sun, a star whose light gives us life. This sun is journeying with 100 billion other stars through our Milky Way galaxy, which itself is falling gently toward its neighbors in the great, silent expanse of the universe. You are a part of this grand, interconnected story. And as you fall asleep, you are not falling into a void. You are simply surrendering to the oldest, most faithful, and most universal embrace of all. Thank you for joining me on this gentle journey tonight. I hope it has brought you a little closer to the quiet wonders of the universe, and a little closer to a deep and peaceful rest. If you have a thought or a feeling you would like to share, I would be honored to read it in the comments below. Your presence here makes this quiet space possible. For more stories like this one, please consider leaving a like and subscribing to the channel. Until next time, may your dreams be peaceful, and may you rest well, held safely in the heart of it all. Good night.